The Manhattan Project, Science, War, and the Dawn of the Nuclear Age. The Manhattan Project stands as one of the most ambitious and consequential scientific undertakings in human history. Conceived in secrecy and developed under the intense pressures of World War II, the project not only delivered the world's first nuclear weapons, but also ushered in a new era, one in which humanity gained the power to annihilate itself. Historical context and early warnings. By the late 1930s, the world stood on the brink of global conflict. Totalitarian regimes in Europe were expanding aggressively, and Nazi Germany in particular was investing heavily in advanced scientific research. In 1938, German chemists Otto Hahn and Fritz Strassmann discovered nuclear fission, a process in which the uranium atom splits, releasing enormous energy. The implications of this discovery were profound. Physicists such as Lise Meitner and Niels Bohr realized that if a chain reaction could be sustained, it might be possible to create a bomb of unprecedented power. Fearing the consequences of Nazi Germany developing such a weapon first, Hungarian physicist Leo Szilard, along with Eugene Wigner and later Edward Teller, approached Albert Einstein to co-sign a letter to U.S. President Franklin D. Roosevelt. This 1939 letter warned of the potential for a new class of weapons and urged the United States to support research into nuclear fission. Roosevelt responded by forming the Advisory Committee on Uranium, a modest start to what would become the Manhattan Project, mobilizing a secret army of scientists. The Manhattan Project officially began in 1942 and soon became a sprawling, nationwide effort, led by two key figures: General Leslie R. Groves of the U.S. Army Corps of Engineers, who managed logistics, security, and coordination; J. Robert Oppenheimer, a theoretical physicist from the University of California, who became the scientific director and intellectual heart of the project. The scale of the Manhattan Project was immense. Over 130,000 people were involved, including Nobel laureates, military personnel, engineers, machinists, and clerical workers. More than $2 billion, over $30 billion in today's money, was spent on the effort. 3 primary sites were established: Oak Ridge, Tennessee, for uranium enrichment using electromagnetic and gaseous diffusion techniques; Hanford, Washington, for plutonium production, using nuclear reactors and chemical separation plants; Los Alamos, New Mexico, for bomb design, testing, and assembly under Oppenheimer's leadership. Despite the sheer number of people involved, the project remained one of the best-kept secrets of the war. Workers were compartmentalized, often unaware of what others were doing. Even among top scientists, access to information was strictly regulated. Scientific challenges and breakthroughs. 2 fissile materials were chosen for the bomb: uranium-235 and plutonium-239. Each posed enormous technical challenges. Uranium-235 exists naturally in only small quantities. The task of enriching uranium, separating the fissionable U-235 isotope from the more common U-238, was both complex and energy-intensive. Oak Ridge became home to vast facilities using calotrons, electromagnetic separators, gaseous diffusion, and thermal diffusion technologies, all racing to produce enough U-235 for a bomb. Plutonium-239, on the other hand, is a synthetic element created by irradiating uranium in a nuclear reactor. At Hanford, massive graphite-moderated reactors and chemical plants were constructed in record time to produce and extract plutonium. However, plutonium introduced a new problem. It could not be used in a simple, gun-type bomb like uranium, because its isotopic composition made it too prone to premature detonation. Thus, a more complex implosion method had to be developed. This involved surrounding a plutonium core with conventional explosives arranged to compress it symmetrically. The concept was elegant in theory, but extremely difficult to execute. Scientists at Los Alamos tackled the challenge with an innovative approach, developing lensing techniques fast detonators, and novel diagnostic tools to perfect the implosion design. The Trinity test. After years of research and engineering, the first full-scale test of a nuclear weapon, codenamed Trinity, took place on July 16, 1945, in the desert near Alamogordo, New Mexico. The device, a plutonium implosion bomb dubbed the Gadget, was detonated at 5:29 a.m. The explosion released the equivalent of 21 kilotons of TNT, creating a fireball that vaporized the steel tower it stood on and turned the desert sand into a greenish glass called trinitite. Observers described the sight as apocalyptic. The shockwave knocked people off their feet miles away, and the mushroom cloud reached 7.5 miles into the atmosphere. The event confirmed what scientists had theorized and feared. The atomic bomb was now a reality. Oppenheimer, witnessing the explosion, later quoted from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." Hiroshima and Nagasaki. Deployment and destruction. At this point in the war, Nazi Germany had already surrendered. The war in the Pacific, however, was dragging on, with the Japanese military fiercely resisting and preparing for a bloody homeland defense. After much debate and a lack of clear alternatives, President Harry Truman authorized the use of atomic bombs against Japan. On August 6, 1945, the B-29 bomber Enola Gay dropped the uranium bomb Little Boy on Hiroshima. The blast leveled 5 square miles of the city and killed an estimated 70,000, 80,000 people instantly, with tens of thousands more dying from burns, radiation sickness, and injuries. 3 days later, on August 9th, a second bomb, Fat Man, using plutonium, was dropped on Nagasaki, killing approximately 40,000, 75,000 people. On August 15, 1945, Japan announced its surrender, effectively ending World War II. Aftermath and ethical reckoning. The success of the Manhattan Project changed not just the outcome of the war, but the trajectory of global politics and science. The bombings of Hiroshima and Nagasaki remain deeply controversial. Proponents argue that they hastened the end of the war and saved countless lives that would have been lost in a conventional invasion of Japan. Critics contend that Japan was already on the brink of surrender, and that the bombings constituted unnecessary and inhumane devastation, especially against civilian populations. In the years that followed, many scientists involved in the project expressed profound regret. Leo Szilard, Joseph Rotblat, and others became advocates for nuclear disarmament. Even Oppenheimer, once celebrated as a national hero, would find himself at odds with the U.S. government during the Cold War. In a now famous 1945 meeting with President Truman, Oppenheimer remarked, "I feel I have blood on my hands." The Cold War and the nuclear arms race. The atomic bomb was initially a monopoly held by the United States, but not for long. The Soviet Union, aided by intelligence leaks from spies embedded in the Manhattan Project, notably Klaus Fuchs, detonated its first atomic bomb in 1949, sparking the nuclear arms race that would define the Cold War. This arms race led to the development of even more powerful weapons, including the hydrogen bomb, thermonuclear, capable of delivering megatons of destructive power. The doctrine of mutually assured destruction, MAD, became the cornerstone of Cold War deterrence. The legacy of the Manhattan Project thus became inextricably linked to the persistent threat of global nuclear war, one that still looms today. Scientific legacy and civilian impacts. Despite its grim purpose, the Manhattan Project yielded major scientific and technological advancements. It pushed forward fields like nuclear physics, metallurgy, chemistry, and computing. The development of early computers, such as those used at Los Alamos for modeling explosive behavior, paved the way for future innovations in information technology. Nuclear energy, a peacetime application of the same principles used in the bomb, became a major area of development in the post-war era, offering a new source of power albeit one that carried its own dangers, as later accidents like Chernobyl and Fukushima would remind the world. Conclusion: a double-edged legacy. The Manhattan Project represents a singular moment in human history, where the boundless curiosity and capability of science intersected with the brutal imperatives of war. It demonstrated that humanity could unlock the fundamental forces of the universe, but also that it could weaponize those forces with devastating consequences. Today, the lessons of the Manhattan Project remain as urgent as ever. As nuclear weapons proliferate and international tensions persist, the ethical, political, and existential questions it raised continue to challenge global leaders and citizens alike. Ultimately, the story of the Manhattan Project is not just about atoms and bombs. It is a story about human responsibility, the limits of power, and the enduring hope that we can learn from our past before it is too late.